Okay, so this is our unconventional look at 10 habits, highly successful oil finders. So the 10 habits are the 10 habits, but we've put some examples in here that are probably a little more appropriate for those of you involved in unconventional. The 10 habits came about from a study that a major oil company did back in the 1960s. And the company noticed that about 10% of their staff routinely drilled dry holes. And by that I mean pretty much any well they proposed became a cement storage facility. About 80% of their staff had the average exploration success rate, which is 10 to 25%. And then the company noticed that there was another group, about 10%, that had a 25 to 75% exploration success rate. And so the company wanted to know what sets the successful oil finders apart. And so they looked at their socioeconomic background, they looked at where they went to school, looked at who their managers and bosses were, they looked at where their plays were. And what they found is that 10% that was successful employed a series of best practices. And so Dan Tierpak boiled that down into the 10 habits of highly successful oil finders. You know, and I teach a lot of young professionals around the world, and one of the things I often hear them say, well, that was the 1960s, I wasn't even born. We have a workstation today. And those workstations can do a lot of things. I can pick my horizons automatically in their workstation. I can push another button, I can get a geomodeler. In fact, I've had geomodelers tell me that I don't need to make a reservoir prediction anymore because I have a geomodeler. And we have simulations. And so that's the kind of thinking that does not contribute to finding oil and gas. But since the workstations now can find the bumps and amplitudes, we still need best practices. So I'm going to take a little walk back through time here, because for us to be successful, we have to make accurate reserve estimates. Because if I think I got 100 million barrels and I invest for that and I only find 20, I'm in trouble. Or if I think I have 20 and I don't invest because I really had 100, then I've lost a good investment. And we also don't make money drilling dry holes. That's Halliburton's job. So let's just go back through time and see how technology's impacted our success rates. So I started in the industry in 1980. We did have computers. They were good for MS-DOS. So as a geologist, I didn't get one. They were reserved for the engineers. So I had a drafting table. And those pencils there, that was my mouse. The erasers, that's my delete button. And then that picture on top, that's the central processing unit. And because we worked by hand, we actually had to think about what we were doing when we interpreted the seismic. We had to think about what we were doing when we contoured our maps, what we were representing with the contours. And we were thinking then about the geology. And at the time, the industry average success rate was just under 25%. So the Gulf of Mexico at that point in time, the exploration success rate was 22%. Then we had bright spots. Came along kind of in the late 70s and were pretty prevalent in guiding our exploration through the 90s. And with bright spots now, all we had to do was to find a bright event on seismic, delineate it on a map, and drill a well. And so with the bright spots, just kind of mentally think where you thought the exploration success ran up to. And if you thought 25%, you were correct. In other words, there was no real significant increase in our success rates with bright spots. And what we came to find out is that there's many things that will cause a bright spot other than hydrocarbons. Shales, marine shales, the siltstone around sandstones, oyster beds. And I know oyster beds cause a bright spot because I did drill one of those that was not in that 46%. And so by focusing on bright spots, we moved away from thinking about the geology. We moved away from thinking about the petroleum system. Then we have AVO, amplitude versus offset. Now AVO is a fluid discriminator. So it is giving us some insight as to what's in the rocks, not just the rocks themselves. And with AVO, what do you think our exploration success rate jumped up to? Actually, it went up to 30%. And it went up a little bit because AVO is a fluid discriminator. But once again, industry came to learn that we can get an AVO anomaly by things other than commercial hydrocarbons. And again, we're focusing on an amplitude or an event in the seismic and not the petroleum system. In other words, we made the same mistake with AVO that we did with amplitudes. Here we are today. We have inversion, we have attributes. We can get more information out of a seismic wavelet today than anyone ever thought possible when I started in the industry. We have really robust workstations now. You can auto-pick and you can and convert your picks to maps very quickly. And then we send them off to the geomodelers. So with our technology today being as robust as it is, where do you think our exploration success rate is? 30%. That was pre-downturn. Right? The downturn has actually negatively impacted the success rate because we're not drilling the conventional things that we had on our plate. We were drilling our high-risk things that had long lead times and commitments to it. So over the last few years, the exploration success rate's actually been lower than 10%. And I suspect in a few years we'll look back and we'll realize that all of this technology today didn't really change our exploration success rates. And I'm afraid we're probably going to make the same mistakes we did with amplitudes and with AVO. Part of the problem is it goes actually deeper than the workstation too. The workstation, as you'll see, is a main contributor to some of our failures. But one of the things I'm seeing is that most interpreters today, they're not learning these techniques in school. They don't have mentors anymore. We fired or laid off all of them. And they don't know the appropriate methods and techniques that they need to know to make valid interpretations and maps. Now also part of that problem is that a lot of those methods and techniques are not taught. They're handed down from mentor to protege. So at lunch we heard the importance of having good mentors. That's always going to be true. Unfortunately, the industry is suffering a major lack of mentors. Again, a lot of the people who've been retired out have said, I'm out, they're gone. So they're not coming back into the industry even to serve as mentors. So the bottom line is we still need these best practices. And these best practices can be summarized in a series of 10 habits. As I go through the habits, you're going to look at the habit and you go, well, that's just common sense. Who wouldn't do that? Well, 80 to 90% of the industry don't do it. That's what we see in the statistics. So, our first habit, successful oil finders ensure that their interpretations are geologically and geometrically valid in 3 dimensions. And I've got this print from M.C. Escher on the screen here. And at first glance, if you look at that, it looks valid. That's what M.C. Escher is famous for. But if you look in detail, some of the columns start in the front of the building and go to the back. Other columns start in the back of the building and go to the front. The second floor is oriented perpendicular to the first floor, which is why the ladder can be on the inside of the rail for the first floor and the outside of the rail for the second floor. So one of the complaints I hear from management is that their interpreters don't understand their maps anymore. And part of that's because it's coming out of the workstation, so they don't have to understand them, which they think. And the other comment is the interpreters don't understand the geology of their plays and prospects. And this is the kind of shortcoming we have that leads to maps that are 3-dimensionally not even geologically valid, but that we see a lot of maps that are impossible from a geometric standpoint. I'll just give you this quick example. So this is a gas field out of the Gulf of Mexico. Map was constructed with a 3D data set and 10 well penetrations. But when you look closely, all those wells with a blue arrow do not match the contours. Or more importantly, the contours don't match the well control. And if you can see, there's a couple wells on there that have as much as 300-foot variation between the contour and the well control. Now this is a function of gridding. So if you're not familiar with what gridding does, it takes your regular distribution of data and it reorders it, and it will often have to calculate points where you don't have many data points. And once the computer's done with the gridding process, it ignores everything you put into the computer up to that point, and it uses its grid going forward, which is how you can get wells that don't match the contours. Another contributing factor to bad maps is the contouring algorithms, right? And there's a couple different kinds. You have deterministic methods of contouring, which are triangulation, equal spaced or parallel, and then interpretive. And I'll argue that the interpretive contouring, which is hand contouring, is the only way you can have a map that you're sure is correct. Now you get your first pass map out of the workstation, you can correct it by hand editing, but you do need to put some hand control in there. Then we have Kriging and Gaussian formulas. So I'll just let you look at this map. So it's a field. We've got a bunch of net pay wells that are wells we're going to contour the net pay. And then there's a number of wells there that have a red number on top. And those are going to be wells we're going to make predictions from. Now, if you're not familiar with what Kriging does, is it basically it predicts the values for the contours to try and fit a curve with as little as possible deviation off the curve. So it's a statistical method. Gaussian tries to fit the data to a normal type distribution around the data points. So here's that map contoured with a bunch of different contouring algorithms. So we have Isochore interpolation, that's a deterministic method. We have inverse distance squared, that's also a deterministic method. Then I have a couple variations of Kriging and Gaussian up there. So if you look at that, you can see there's a considerable variation in how those maps look. Remember, we're contouring net sand. So if I go to those locations where we're predicting, if you just look at the bottom number, the delta there, for location A, I have a 90-foot delta between my predictions, right? So imagine you've got this field, you're going to go to management and say, I want to drill location A. Now you might find 9 feet of pay, but I also might find 100. Now this is a development with a lot of wells. It's not really an acceptable prediction to management. The problem is, there's the correct map, hand contoured. It was a meandering river. Not one of those maps represented a meandering river, which goes back to one of the comments I get from management. My people don't understand the geology. They just pushed the button and got contours. No one went back and said, well, do those contours look like my depositional environment? And it turns out machine contouring does a very, very poor job of contouring sands. So you almost always have to contour sand maps by hand, and it cannot contour a meandering river. Right? It can if you put in a few thousand points. Right. Our second habit, successful oil finders have a strong background in geology and a thorough knowledge of the tectonic and depositional settings for the environments they're working in. That goes back to the example I just showed. If the interpreters understood they were looking at a meandering river, they wouldn't have accepted any of those maps coming out of the workstation. We can contour any element. So here's a map of the Eagle Ford Shale. It's the total organic shale content. But to contour that, you have to know what's controlling TOC. Right? Otherwise, it's just a basic map. So I can contour this case. I've got the upper map's formation pressure. The lower map, CO2, is from a play in Southeast Asia. Well, to contour CO2 values, you have to know what's causing the CO2 to begin with. But once you understand that, you can contour them. Our third habit, successful oil finders plan their time and their work in order to ensure accurate interpretations in maps. Now, as an interpreter, unless you're senior management, you have very little control over the time, right? Management will tell you the time frame. But a lot of you see this sign is usually on a secretary's desk. Poor planning on your part does not constitute an emergency on my part. However, poor planning does result in dry holes, and unfortunately it results in a lot of them. In fact, the fastest way to guarantee drilling dry holes is to have 6 prospects and take a rig contract for 12. Right? Every time people do that, the dry hole count goes up at the end of the drilling program because you're advancing things into drilling schedule that aren't really ready to go. So kind of think about how we work. Kind of the 80% of our unfocused effort gets 20% of our results, then the deadline's looming near, and so then 80% of our results comes in that last 20% of effort. Avoid that. Plan your time out in advance so that you know where to focus your time. To do that, start with the end in mind. What information you need for the decision, and make sure your work addresses that. How much data do you have to evaluate? How complex is the geology that you have to assess? When is the decision really due? Not when management asks for it, but when's it really due? And what's the impact of that decision? If the decision is $1 million decision to buy more data, you can have a little flexibility in your interpretation. If it's a $1 billion platform, you need it pretty tight. So plan out and prioritize your work as the ideal, not with your deadlines. Then after you have the ideal, if you don't have the time given to you by management, you go sit with that plan and say, what are we willing to compromise on? Because every compromise you make in the plan increases the risk of a dry hole. And if management's willing to accept that, document that, by the way, but then go with that. But again, make sure you know where to focus your time. Our fourth habit, successful oil finders use all of the data to ensure they have reasonable and accurate subsurface interpretations. We are a data-intensive industry. We have engineering data, we have pressure data, we have well log correlations, structural geology, seismic. All of that has to come in and fit one single interpretation that honors all the data. And one of the things we see is that the failure to use all of the data is one of the major contributing factors to getting dry holes drilled. Now that kind of goes back to the last habit, right? It takes a lot of time to go through all that data. But if you don't, you got to love cement. So now one of the challenges people working on conventional places, they have thousands of wells. Some of those places have 10,000 wells. You can't possibly correlate that in any kind of time frame management is going to give you. So we have a technique that we teach at SCA called delta D over D. And you can use that to identify at least wells that have the potential to be miscorrelated, so you can go back and focus only on the problem childs. And all delta D over D states is that I have well 1, that's my reference well, and I'll have an interval in there that I'm going to measure the thickness. Then I go to my next well on this trend, well 2 in this case, and I'm going to measure the change in thickness, or delta D. And if I have a small delta D, it means that basin is developing rather slowly, not much going on. But if I have a large change in interval thickness from well 1 to my next well, then I have a steep slope on my plot, and things are happening fairly quickly. So there's a couple of steps that you need to make a delta D over D plot. First is take your correlations, or make your correlations, and then second, put them in a spreadsheet. And you should be doing that anyway, which is one of our last habits. And then develop the graphical display. And I'll show you the display in a second. Then you're ready to interpret the results, and you're ready to apply the results to refining your correlations. So here's a way one of the delta D over D spreadsheets can look. There's other ways to do it. So in the yellow column, we're plotting the sand. So you can see it's a Gulf of Mexico well. So we got Frio A to Frio X. The depth, so the 382 number 1 well in the blue column, that is the reference well. So in the reference well, we post depths. And then in the well we're comparing back to the reference well, the Unical number 7 well, they posted delta D. Here's the plot then of those two wells. So what you see there is the red line represents the various sands from the Frio. The horizontal axis is the depth in the reference well. The vertical axis is the change in thickness. And so you can see we've got a fairly uniform slope. There's a few changes in the slope that tells you a little bit about the basin history here. And if you're familiar with the Gulf Coast, many of you here are, what you know is that as you go to the end of the Frio, we start going into the major transgression that formed the Anahuac Shale. And you can actually see that in the change of slope from Frio C to Frio A. Well, one of the things that you can do with this is if you can see your correlation should line up reasonably well. And if you look at that correlation point number 27 here, right toward the top, you notice it doesn't plot on that line or close to the line. That's an indication that that marker that was correlation 27 is miscorrelated. So if you make a delta D over D plot, and you can do it for multiple wells, I'll show you that in a second. Any points that you see that don't really fall in the line, those are your suspect correlations. So instead of having to go back and look at 10,000 wells, you get your delta D over D plot and find the few points that you need to go pay attention to. And here's what a plot looks like for multiple wells. So the gray squares on the bottom axis, that's the reference well, which is the number 6 well. And then we have all the other wells. And this is on the flank of a salt dome. And so you can see that all the wells plot reasonably well, and where you see, or parallel, and where you see breaks in the slope, that's telling you something's going on. So we've crossed an unconformity, or we've crossed a fault. And then you can see where the slope is steep, that's when the salt dome is actively growing. When it's flat, it's very little growing. And then we have that time hiatus there that gives us that change in slope there. So you can start to put together the basin history as well. So it's a pretty powerful tool. Our fifth habit, successful oil finders ensure that their seismic and well log correlations are accurate and loop tied. And this is just as important for unconventional as it is for conventional. And when we auto pick our seismic now, we're letting the machine do our correlations for us. And if you're going to do that, at least go back and make sure, hand check a couple lines to make sure they're properly loop tied. Remember, when your computer's doing your correlations for you, it's not a geologic correlation, it's a statistical correlation, right? So I'm at digit 1 and I'm going to look at all the digits around me, I'm going to compare them and I'm going to go to the digit closest to me and I'm going to do it again. And that's what computers are brilliant at. Multiple mathematical computations, millions and billions a second. But they don't know squat about geology, right? I'm going to give you an example from a conventional opportunity because I think it's one of the neatest ones we've ever seen. And this came from a unit hearing in Louisiana. And so Company B has the lease offset to Company A. Company A drilled these 3 wells. They've got some sands in production. And Company B asked for a unit hearing because by their correlation, Company A's production extended onto their lease. And they were asking for about 40% of the total production. And the geologist from Company A went in the unit hearing and said, well, you know what? We don't agree with Company B's correlation. There's our correlation. And what they have done is they went in here and made a very detailed correlation of the shale, all the resistivity markers, and they found a 50-foot fault in each of these wells in the shale between sands 5 and 6. Now the impact of that is there's the map. So their position, and the judge agreed with them, is Company B might very well be in communication with Company A, and they probably are, because this fault has less offset than the sand thickness. But Company B had to drill their own well. They had to prove that they were in communication with well A, or Company A, at which time the company would form a unit. But if the geologists from Company A had missed that fault, then they would have given up 40% of the production of the area shown here in green, not for the entire area. That's the only production that's been established. And so that detailed correlation in this case saved them 40% of their field. I often have geophysicists tell me, by the way, well, that's a 50-foot fault. I'm not going to see that on seismic at this depth unless I have really good 3D. So it doesn't matter. And I said, well, I'll tell you what. You go up to the 5th floor of any building you want, jump off, and think about whether 50 feet's a big deal on the way down. Our 6th habit. Successful oil finders know the methods, tools, and techniques that you need to define and understand the subsurface. If you've got faults in your area, you've got to make fault surface maps. You want to make illustrative cross sections. You want to look at restored tops if you have wells that cross faults. You want to use the geomodels, and you have to make sure you're using TVT values for net pay or net sand. Now, there's enough methods and tools and techniques that it takes us a full week to teach them, so we're not going to cover really touch on them here. I will give you one thing that we have to make sure we do, and that's to make sure we're using the right fault terminology and use restored tops when we have faults or wells that cross the faults. We have a lot of money lost in this industry because we don't use the right terms. And we very commonly mistake the word throw when we really mean vertical separation. So throw is, I'm not even going to go through the AGI description because it's hard, I don't even understand it. What throw really is the depth of the upthrown intersection of the horizon with the fault minus the depth of the downthrown intersection of the horizon and fault. So it makes a right triangle. Vertical separation, I'm going to take my horizon from the downthrown block and project it with the same dip rate until I get to a point below the upthrown depth intersection with the fault. That's the definition of vertical separation. If I drill a well in the fault gap and I determine the amount of missing section, that is the vertical separation, not throw. Now I can also use restored tops. So in this case, I've got a well on the upthrown side of my fault, a well on the downthrown side, and the well in the middle is in the fault gap. If I'm making a map on the orange horizon, I can calculate the restored tops through a log correlation process. But the upthrown restored top is the position in that faulted well where horizon would occur if the fault wasn't present. Likewise, the downthrown restored top is the position in that well where the downthrown horizon would have occurred. So here's a case where people lost money because they confused the terms. So we've got well 7 is in the fault gap. And this is a field that's got a lot of producing horizons. But they correlated well 7 to well 8, which found that same sand had a water level. And they correlated to some of the upthrown wells that are producing. And they recognized that they had 1,000 feet of missing section. So what they did is they came down 1,000 feet from the upthrown block intersection, came over to the fault and said, we're going to drill a well to get the downthrown block. And they drilled that well, and it was a dry hole because the horizon was faulted out. So then they had to drill a sidetrack, and they found the horizon. There's the horizon in its correct position. So the cost of the sidetrack was necessary because they had misapplied the term throw. So when the geologist said I have 1,000 feet of missing section, they should have projected the horizon across the fault until they got to a point above 1,000 feet above the fault and projected the horizon there. So there's the correct position of the horizon, and they would have then just put their well in the correct position in the first place. Then they also could have calculated the upthrown and downthrown restored tops. It's about a 10-minute exercise with log correlation once you know how to do it. That would have saved them the cost of the sidetrack, because it would have put the downthrown block in the proper position in the first place. For unconventional, where we see this as an issue, is when we're drilling our horizontal, we get to a fault, and the geologists come back and say it's a 100-foot fault. So we come over here, we come down 100 over to the fault and project our horizon there. Driller comes in and they land the well too shallow. So now he's got to drill the well or deepen the well. And so there's where he thought he was going to enter the horizon. There's where he actually entered the horizon, and all of that red line there is opportunity that was left not exposed to the wellbore because we confused vertical separation and throw. If they'd have done it correctly in the first place, they would have projected across at the same dip, come down 100 feet, and then the driller could have landed right in the zone where he wanted to. Our 7th habit, successful oil finders map all relevant geological surfaces. If you've got unconformities, you've got to map those. If you've got faults, you have to map those. Well, we have a lot of unconformities in a lot of our unconventional plays. You have to then map not just the unconformity, but the top and the base of your key target sections. So here's an unconformity section, and I've got a resource below it that's truncated against the unconformity. If they've only mapped the unconformity in the top of the target zone, this is where they're going to plan their well. Come in close to the top, right below the unconformity. The problem is we have an unconformity wedge that we have to account for. And if we're not drilling in the wedge, we're going to leave behind a lot of reserves. So you really want to have a map of the top and the base of the reservoir, and then define the wedge, and then bring your well in closer to the base, not the top. Our 8th habit, successful oil finders map multiple horizons, and they make cross sections to develop reasonably correct and three-dimensionally valid interpretations. So an application of this in unconventional plays is what we call multi-surface stacking. So if you look at the top horizon there, all those wells penetrate the upper horizon, so we have good control on how that looks. For the lower horizon, the blue horizon, we have only 4 wells that penetrate that. So if I make a map of the top horizon, then I can see I've got a really good control on the structure. Because I have less penetrations, if I just use the well control, then I've got a map that looks like that, and then 2 maps don't have contour compatibility. They don't look the same. And then if I make the Isochore map, I can now come back using the Isochore data and to get more control on my lower horizon. That gives me a better map of the lower horizon. So when I'm coming in to drill, I know the thickness between horizon A and B, and I know the thickness between B and C. So I've got my cross section planned here, and so I'm drilling my well. I encounter A pretty much where I wanted to or expected to. When I get to formation B, it comes in a little bit low than I expected. So what I can very quickly do is then adjust my tops for A and C. Now I have an adjusted top for C, and I can go back. The driller can then redirect the well to come into formation C on target. So the other thing, now that method relies on what we call an estimated top. It's essentially a restored tops for wells that TD above horizon, or we see the horizon not reached. So here's a cross section should have shown this to Jeff. There's some opportunities in here. Anyway, we have a couple wells here that are not reached. But I have enough well control that I know the interval thickness between the horizon that I'm making the map on and my shallow horizon, so we can come in here, use that interval thickness, and then predict where that horizon would come in for my not reached wells, and that could either help for play development or for prospect mapping or just getting the maps right for the horizon. Our ninth habit, document your work. Right? It's especially important today because we have so much data that we have to collect, and if you're ever audited, God forbid, one of the first things an auditor is going to ask you is, let me see your documentation. They're going to want to know how you got your estimates for reserves. And we have, again, I said, a lot of data that we have to incorporate in our interpretations and in our assessment of reserves and resources. So we want a good, accurate recording of the data, and you want to document what you did and how you did it, and if you can, why you did it. Because, again, it's just, if you ever need it someday, it's going to be there, and I guarantee you the time you need it will be so long after the time you did it, you won't remember half of it. So we document faults, so the depth of the faults in any wells. We also do it with the seismic. We put, for key mapped horizons, we also calculate the restored tops on there. We do it for formations, so all the information we record for formations you can use for delta D over D. If you have, we also have enough information in there to calculate the TBT so that you get the right values for net pay. Our 10th habit was kind of brought out a little bit in the earlier talk, get mentors. Right? It's harder today, but there's still plenty of gray hair in here. In fact, I see almost all gray hair. So for those few of you in the room that don't have gray hair and aren't coloring it, find someone with my hair color and ask us to be mentors. Right? And there's plenty of us that are still around, and almost all of us would be rather pleased to serve as mentors for you. And be mentors, right? I mean, we had a young speaker for lunch. He sounds like he's the kind of guy who will be a mentor. He's already a mentor, so. But you'll have to make your own networking opportunities today. You're not going to get them in companies like we used to. We have APG, you have HGS, we have SIPES. So a lot of resources are available to you to find mentors. All right, so those are the successful habits of oil finders. If you use them, if you take these habits on board, you will increase your exploration and development success rates. And we've seen it time and time again. You can use them individually. If you're a team lead, you can use them in your team. If you're a manager, you can bring them back and make the company do it. If you don't adapt them, right, that's your choice. You can continue to generate poor quality, geologically inappropriate, and three-dimensionally invalid structures and interpretations. You can reduce your effectiveness, and you can continue to keep Halliburton stock up high. All right, and you can get our 10 habits talk, the conventional ones, on our website. You can also look at our classes. We also have a number of webinars available to you, so you can go in there and be entertained for 20 or 30 minutes free of charge. All right.
So my question to you is, when you meet someone who's drilled a dry hole, or you talk to management, they've drilled a dry hole, but they don't want to admit it's their process. They just want to blame geology, or just blame, it's just we have to take a risk, it's a risky business, that type of thing. I mean, how do you discern, or how would you communicate to a company that it's really their process that's flawed, rather than just this risk thing that everyone has to agree to?
Okay. Well, at AAPG, I gave a talk on how bad maps equal bad investments. And what you see when you look, the look-back studies have been published. They generally state that that 50% on average, 51 to 55% of the dry holes are a result of trap and seal failure. 25% reservoir and 25% charge. So just taking those statistics, you kind of get the feeling, well, half of my dry holes are the result of a petroleum system failure, which is our failure, right? We didn't properly assess the petroleum system. And the other half were trap and seal. But you have to understand what a look-back study usually means, right? So we predicted we would find X reservoir at X depth with oil or gas. If the reservoir was present, it was not a reservoir failure. If there's any kind of show, or if I'm next to a field that's not charged, so then it becomes trap and seal. But a couple of other studies, one by Dan Tierpak and another one by Loiseau, went back and actually looked at the maps themselves. So they audited the maps. And what they found is that a majority of trap and seal failures were maps that were so poor that what the company was drilling was not what they thought they were drilling. And so it really comes down to probably not quite 50%, but a majority of our dry holes are dry holes based on bad maps. So the company needs to do an appropriate look back, right? Not just blow it off. They have to say, okay, and there's two elements that you can do to validate the structure. The first is, if I predicted a horizon at 10,000 feet and it came in at 10,000 plus or minus 10%, that was probably okay. If it came in on more than 10% variance, then you need to look at the pre-drill and post-drill velocities. And if there's significant variance in those, then it could be just depth conversion. But that will change your structure map. So you're going to want to remap the structure with the new depth control. The second thing is check the pre-drill and post-drill dip. So if my contours indicate that I was going to drill this structure where I had north dip at 5 degrees, and I had northeast dip at 7 degrees, I know my map's wrong. Those are real easy to check. If you have that kind of variance, then you got to go back and remap and look at what you really drilled, right, using the appropriate methods and techniques. But that takes effort, right? And a lot of companies don't want it. A lot of companies seem to have the mindset, well, that money's gone, I'm not going to get it back, so let's just move on. I look at it as, look, you just made a multi-million-dollar investment. I think you'd want to take every opportunity you can to learn from it so you don't do it again.
Is there any more questions?
Yeah. So, Bob, how much variance do you see in big companies as to lookbacks? Is it all pretty standard, or is there just a wide variance? And then, how do you see independence? How methodical are independents?
Okay, it's easy. I can answer the first part of the question. The standard for lookbacks is pretty much in big companies the same, right? We focus more on the AFE element of it, right? Days drep, geopressure prediction, and again, if I had a probabilistic distribution for my net pay and I found net sand but no pay, did I fall on my distribution? I have not seen any company that really systematically goes back and says, all right, I want to double check the map and make sure the maps that were the basis of my prediction for the prospect were correct. And that's just because the companies today are resource constrained, right? Everyone's working about 1.5 times more than they should be. As for independents, I don't know. I don't get to talk to independents. They don't hire us.
Just out of curiosity, has anybody had a business model to just go following behind companies? They don't have all the data, but just looking for mistakes.
Not that I'm aware of, but there's a couple places that I think lend themselves particularly well to going in after dry holes. I was in a talk or a forum on rift basins a couple weeks back, and Karen in India got up and gave a great talk of a basin that they'd opened up in the last decade that's 6 billion barrels. And that basin had a bunch of dry holes from Shell. And there was one table commenting that an excellent exploration strategy would just be wait till Shell leaves and then go in behind them. So there's one example. And that's probably true of a lot of the big companies. There's very low tolerance for dry holes in companies, and oftentimes it's one dry hole, we're gone. A few have staying power for 2, but in the case of Karen, they went in after a dozen. And if I remember the statistic right, before the Gulf of Mexico really opened up, there were almost 100 dry holes. So you have to have you have to kind of have a play concept that you think will work and then see if they're actually testing that, and oftentimes they're not. So I think, there's a lot of opportunity. I mean, that sounded like a lot like what Jeff is doing, right? So you've got a bunch of 3D in an area where there's a bunch of old fields, and he's going in and finding opportunities that were either missed or exploited. So I'll give you a great Bob Snyder story. So when I was about 10 years into my career, and I'm thinking, all right, I'm ready to go do what Snyder did, and that's buy a bunch of production and make a ton of money. And I was on a field trip with him. I asked him how he knew what fields he wanted to buy. He says, it's actually pretty easy. He goes, if the exploration office and the production office are in different cities, I'm almost certainly going to buy their production. If they're in the same city but different buildings, I'm likely to look at it and buy it. If they're in the same building and different floors, I'll probably look at it, but I don't think I'll buy it. And if they're on the same floor, I'm not even going to look at it. And I'm sitting there in the bus going, well, I sure as hell can't take that to a bank and get money. And it didn't really hit on me as to why that was significant until I started teaching our mapping class and our habits and got to the habit where people aren't using all the data. And his point was, if they're in different cities, they're not talking. So one of two things happens in their development. It's overdeveloped or underdeveloped. Right? So he can look at the deal and very quickly see if it's overdeveloped, and then he won't buy it. And if it's underdeveloped, he's not going to spend a lot of time doing the reserves. He just knows he's going to get opportunity out of it. And if you marry that with what Hillcorp and Samson do, and that is just clean up the geology or the jewelry and increase the existing production and flow rates, and know that you're going to find additional opportunities, it was a great business model. Yep.
If you look at the history, I mean, we're about the same age, and I remember when I first started, companies I worked for, a certain amount of their portfolio was rank wildcat exploration, whether it be international or whether it be domestic. As I've moved through my career, the number of companies of that nature have diminished, combined, and so there are less exploration wells being drilled. And certainly more recently, over the last 10, 15 years, we have focused so much on resource plays that there's very little exploration wells being drilled on there. So when we look at things over our lifetime span, there's been a quantum change in what's physically being drilled. And, you know, that leaves for the independents, you know, the exploration wells to be drilled, but they have the same challenge, is finding somebody to fund those wells to actually drill on there. So, you know, when we look at statistics, I was struck by when you look at your success rate. You know, it was kind of like it really didn't change that much over time, even with 3D seismic, even with AVO. It didn't change that substantially. Yes, it improved a little bit, but it wasn't like, you know, the 80% success ratios that we were quoting. And so I think when we look at these things, we don't look at them correctly in terms of the category they are. Are they exploration? Are they develop cap? Are they development type wells? You know, is that an experience? I mean, is that a fair assessment?
Yeah, I think so. I mean, going back to the statistics, I mean, and one of the things that got me started in this is I presented a prospect to management, and we'd given it like a 25% chance of success. And another team had a prospect that was very, very similar, and they were giving it a 70% chance of success. And I said, wait a minute, there's no way in hell that that's got a 70% chance of success. How did you get that? And he goes, it's got an amplitude. I said, yeah. He said, well, we did a study where anything that had an amplitude, you know, we had a 70% chance of success on it. I said, and I was around when we were drilling some of those earlier wells, and I went back and got the statistics, and what they'd done is they'd fixed the numbers, right? So a number of dry holes that were drilled on amplitudes, they said, well, that wasn't the amplitude supported. Well, why not? Well, it was a dry hole. So very circular logic, and so some of those very high advertised success rates, that was marketing. But I think we had this conversation earlier in the back. We're going to have to, as a country who needs energy, we're going to have to start getting investments back into more conventional opportunities. We just can't keep drilling 10,000 wells in our resource plays a year and expect that to continue for another decade. Or we're going to start drilling 20 feet spacing. So we're going to have to start going back, and I think the investment community will recognize that in time. At least I hope they do. And they're going to go where opportunities are, and they're going to start seeing opportunities come back in the conventional place. I mean, I live overseas. We don't have the unconventional, so for me, it hasn't changed that much.
One more question for Bob.
Okay.
Bob, I'm old school Texaco, and when I learned to prospect, I learned it from people that knew how to prospect.
Yeah,
Find all the games.
Same here.
So my question is, where are our young petroleum aspiration geologists learning the craft or the trade? It's not being taught in the universities.
Nope, and they're
I
not.
don't think it's being taught by the major oil companies.
No, they're not learning it.
So where are they learning?
They're not, and that's one of the other things I see. I'm going to come back and give you a Texaco story too. So we've got a huge capability gap in our industry. We have a capability gap with the geoscientists because they don't know what they need to know to find prospects. And if we don't fix that, the dry hole counts are going to go way up. We also have a capability gap in the engineering community because they also aren't getting some of the critical skills they need. And if we don't fix that, we're going to have another Macondo.
Well, that's a major challenge. I believe we can all think about some solution to.
It's a major.
They're not taught how to find oil and gas or where it is or why it's there. We got a problem.
No,
a big problem.
And we do have to address it as an industry or we are in trouble. So funny Texaco story. I gave our 10 Habits talk in New Orleans a couple years back. And the guy come up to me after the talk. He says, I'm ex-Texaco. He said, in our office we had 5, not 10%. I go, 5% is pretty good. I didn't mean 5%, I meant 5.
People.
Yeah. So that oil finding group's a small community, and it's the ones that do learn how to, basically think with a pencil.
So good deal. So
I'll get you after.
One comment. I had a guy